Alright, so let's take a little time here to look through angles between vectors and direction angles. And so we'll start here back with the geometric version of my definition for a dot product. U dot v is the magnitude of u times the magnitude of v times the cosine of the angle between the vectors. So there's a picture of two vectors with the angle between them. And with any two vectors, whether you're in 2D or 3D, you can always identify that there is one angle between them between 0 and 180 degrees. So that's a key fact here, is that any angle between vectors would always be between 0 and 180 degrees if you're measuring in degrees, or between 0 and pi if you're measuring in radians. So you could think of it as once you pass 180 degrees, then you could just measure on sort of the other side of that pair. You could think as soon as this angle passes here's 180 degrees. As soon as it passes 180 degrees, I could just switch theta, say theta is over here. So always between 0 and 180 degrees, or 0 and pi. And this is true whether you're in 2 dimensions or 3 dimensions. And part of that, the point of that is that as soon as you identify two vectors, you're actually identifying 3 different points in space. Right? If you put those two vectors with a common starting point, because if you have two vectors, you could always bring them together with a common starting point. And so once you have a common starting point, then there would be 3 points. And those 3 points would always identify a plane, always form a plane in 3-dimensional space. So it's within that plane in the 3-dimensional space. In the plane, those two vectors form an angle, and it's that angle between 0 and 180 that is that unique angle that's always the angle between any two vectors. So we can rewrite this relationship with the dot product in this form. And so we could use cosine inverse to solve for theta if we actually wanted to find the angle. The good thing about the cosine inverse is that its range is 0 to 180, which is precisely what you would need. So you would never have to correct for some restriction on the angle from the definition of cosine inverse. You could simply always find cosine inverse of this u dot v divided by magnitudes of u and v. And this would always produce exactly the right value for theta, whether you have it in degree mode or in radian mode, if you use a calculator. And sometimes you can actually recognize whether it should be 0 degrees or 90 or 180 just based on the value that you get here. And I'll get to that in a little bit later in this video. Actually, I'm kind of getting to that point really in this slide. Okay, it's here that we can sort of see some of the basic different things that can happen with respect to the value of a dot product. You might have an instance where, let's say the angle was 180. So I'm looking at this picture here. If the angle is 180 degrees between those vectors, then in the case that the angle is 180 degrees, the cosine is going to be -1. And when the cosine is -1, you can see that the dot product actually corresponds to just the magnitudes of the vectors times each other times a -1. Another thing that could happen is that the angle might be between 90 and 180, that is, between pi over 2 and pi. In that case, the dot product's a negative, and that's because the cosine is negative in that interval. It's between -1 and 0. But it isn't either of those endpoints when you're restricted between 90 and 180. It's possible that the angle between vectors is exactly pi over 2 or 90 degrees, and that would be this case. In this case, when you have the cosine of pi over 2, you get 0. And the cosine in this formula, pi over 2, when that's 0, then the dot product is 0. And a nice word to learn at this point is orthogonal. When you refer to perpendicular vectors, well, you can use the word orthogonal. Another thing that could happen is the angle might be between 0 and pi over 2, or 0 and 90. In that case, cosine is positive and it's between 0 and 1. And so we end up with a dot product that's positive. So you could even identify, if you see the dot product of two vectors as positive, you know the angle between them is between 0 and 90. And if you saw the dot product was negative, you know that angle between the vectors would have to be more than 90 but less than 180. Right? And the zero dot product, immediately need to recognize that's a 90-degree angle. Those are orthogonal vectors. Another thing that could happen is the angle between two vectors might be exactly 0. In that case, because the cosine of 0 is 1, you end up with just the dot product is just the value that comes from multiplying the magnitudes of the two vectors together. And that's what you can see visualized in this picture. So the other thing that I have drawn here is a setup of how you might try to explain what does the dot product look like, a geometric understanding of a dot product. There's an algebraic one, but if we take a moment to look at visualizing a dot product, we could say that the dot product corresponds to, let's say, the length of the vector v times the length of the component of u in the direction of v. Or I should say parallel, right? Because it doesn't always have to be in the direction, right? Like over here, I'm going to say the dot product is the length of v times the length of the component of u parallel to v. Yeah, that's it. The length of vector v times the length of the component of u parallel to v. Length of v times the length of the component of u parallel to v. That's a mouthful. Alright, so let's continue on with the ideas of direction angles and direction cosines. I always think of the ideas of, like, maybe you'll be doing some design on a computer, engineering design, maybe game design, or even like looking at camera angles in a movie, and you basically have to say this way, point some direction, and maybe you need direction and also some distance, or maybe you have you're modeling something with a particular force in three-dimensional space in a particular direction, or a velocity or an acceleration, and it has a direction, it has a magnitude, but you got to get it on a computer. You can't just say that way. Right? So if you're going to get it onto a computer, you need to put it into some sort of a measurable form, computable and calculated form, and so we can talk about directions and vectors and magnitudes of these vectors in 3D space with this language of direction angles. It's just like having a theta when I was in 2 dimensions, but I need 3 different angles to create sort of the most useful, easiest way to describe a direction. So we're going to consistently use alpha as the angle between the x-axis and some arbitrary vector v. Right? So it's equivalent to saying alpha is the angle between I and an arbitrary vector v. Right? So you begin with some vector that's v that goes in some arbitrary direction. Alpha is the angle to the x-axis, beta is the angle to the y-axis, or j, and gamma, that's the angle here, gamma is the angle between v and the z-axis, or the unit vector k. So these are direction angles. Direction cosines are the cosines of each of those direction angles. So to develop a little further how this actually works, let's create an arbitrary vector v, points in some arbitrary direction in 3-dimensional space, and the components in the standard form for a 3-dimensional vector we'll call v1, v2, v3. These are the x, y, and z components of this 3-dimensional vector. You can write it in either of these forms. They're equally good, perfectly correct. Both of them are equally useful and important. So now to proceed from there, what I'll do is say, if you recognize that alpha is the angle between the vector v and the unit vector I, if that's what alpha is, then from this work that we had started at the very beginning, this is why I did this to begin with, is I could say the cosine of any angle can be written as the dot product of those two vectors divided by the magnitudes of those two vectors. And so if that's true for any angle theta, it's true for this angle alpha. I'm going to use alpha exclusively for that angle between I and V. And so between the unit vector I and the arbitrary vector V, cosine of that direction angle must equal this I dot V over magnitude I magnitude V, as I've written here. Well, the dot product of I with V would be the dot product of the vector 1, 0, 0, that's the vector I, dot, here's the vector V written out in its component form, V1, V2, V3. And if you do a dot product of these guys, you're multiplying the x component with the x component plus y component times y component, that's 0. Z component 0 times Z component V3, that's 0, and you add that together, you just get V1 as the result of this dot product. So that's V1, the x component only, a scalar divided by V, the magnitude of the entire vector, which also is scalar. So the cosine of alpha is this scalar ratio. And so that's an important point to recognize, and now I can do that for all of the other two angles. So just to make sure that that's clear, I'll go through that one more time. See, I'm just following that same pattern. Beta is the angle between J and V. And therefore, the cosine of beta is J dot V over magnitude J, magnitude V. Magnitude of J, just like the magnitude of I before, is equal to 1, and that's an important point I should have said before. This disappears because it's magnitude 1. So we're going to end up with cosine of beta is, here's J, and then we can do the same thing for gamma. So the cosine of gamma is V3 over V. So we can stop for a moment and just summarize that conclusion there. For any vector V in three-dimensional space, the direction cosines are cosine alpha V1 over magnitude V. So V1 over magnitude V is the direction cosine. You don't literally have to see the word cosine there. You could say that this ratio is the direction cosine, one of the direction cosines, and V2 over magnitude V is another direction cosine. It's the direction cosine for the angle beta, and cosine gamma is a direction cosine equal to V3 over V. And the direction angles are those angles alpha, beta, gamma that you could find by doing cosine inverses. Okay, so there's another point that I want to make here, and that would be that we could start with that vector V, V1, V2, V3, and what I'll do is I'll factor out the magnitude. And the way I'll do that, what I'll do is I'll say this represents the magnitude. And if I write it out front, then I'll just put it in the denominator in each of these components so that I haven't changed the value of the vector. So this is magnitude. This is a unit vector. This represents a unit vector in the direction of V. I've mentioned this in a previous video, I think, how I was talking about sort of a familiar form that we can talk about a magnitude for the vector and a direction. And we can specify the direction as a unit vector, and that's what we have here. This would actually have, this vector is a unit vector because we see it dividing out by the magnitude. And each of those components in that unit vector, now you can say, oh, those are the direction cosines. These three components are the direction cosines. So the components of the unit vector that specifies the direction, they are the direction cosines. And now we can write that vector, this is V, arbitrary vector v as the magnitude of v times this guy is the cosine of alpha, this is the cosine of beta, this is the cosine of gamma. So you can see the unit vector that corresponds to the direction of v written in terms of those direction cosines. They could be cosines of some angle that we might find, or they might be just those ratios of those numbers that we might refer to as a direction cosine, either the actual cosine of some angle or just the ratio. And what this is a unit vector here, and since this is a unit vector, its magnitude is 1. And that leads us to another important conclusion, which is that the cosine squared of alpha plus the cosine squared of beta and the cosine squared of gamma, since the magnitude is 1, if you take the magnitude of this vector, it would have to be 1. Squaring both sides, I get this equation. This is a pretty neat little result that I always think of sort of fundamental nature of the universe. You could say fundamental nature of three-dimensional space, that the relationships between the direction angles alpha, beta, gamma for any particular direction you specify in three-dimensional space, the relationship between those angles, alpha, beta, gamma, will always satisfy this equation. So in particular, if you knew 2 of those angles, you could find the third. I want to just lastly highlight how in two-dimensional space, I might have done something like magnitude of v, and then say cosine of theta I plus sine of theta j, and in that case I was just using one direction angle because I used sine and I didn't have to do cosine of some phi, some other angle. This is in 2D. And now in 3D I have a similar form, but it's just normal to go to 3 different angles. So magnitude of v, and we'll say cosine alpha I. See, I'm switching to the unit vectors, so I'm going to use pluses. Cosine beta j and cosine gamma k. These are similar forms in that we are looking at a magnitude and a unit vector that specifies direction to uniquely determine a vector. Let's move on to an example. This one says, find the direction cosines and angles for the vector v equal to 2i plus 3j plus 4k, and show that this property cosine squared alpha plus cosine squared beta plus cosine squared gamma all equals 1. So if you calculate the magnitude, you get square root 29. You could then find each of the direction cosines by using these ratios, v1 over v for the direction cosine for alpha. So I could say that 2 over root 29 is the direction cosine, and 3 over root 29 is another direction cosine. 4 over root 29 is the third direction cosine. It's the direction cosine for this angle gamma. So if I wanted to, I could then find each of the angles alpha, beta, gamma using cosine inverses. So that's what the question asked for. Find the direction cosines and angles. So we have the direction cosines 1, 2, 3, and the direction angles here 1, 2, 3. I just want to write one last thing, that this vector that was given, v, equal to, it was a 2, 3, 4. In finding the magnitude of square root 29, we could then say this is 2 over the square root 29, 3 over square root 29, and 4 over square root 29. So there's the unit vector that specifies the direction. This is the magnitude of the vector, and together they form the vector. Lastly, we were going to confirm that these cosines, this equation is true. So because the cosine of alpha was 2, right, the cosine of alpha was 2 over the square root of 29. Squaring it gives me 4 over 29. And since the cosine of beta, that was 3 over square root of 29. Squaring that gives me 9 over 29. Cosine gamma, that was 4 over square root of 29. So yeah, squaring that gives me 16 over 29, and that adds up to 29 over 29, and that is 1 as it should be. And finally, here's a picture. You can see where alpha, the angle alpha, we measured that to be about 68 degrees. So the angle in that plane that contains v and the unit vector I somewhere down here, I would be something like this. In that two-dimensional plane, the angle alpha is about 68 degrees. And if this is the vector j, in the plane that contains the vector v and the vector j, in that plane, that beta, that angle beta, we found that to be about 56.1. And gamma, the angle between the z-axis, or the unit vector k, and k would be somewhere like here, that angle gamma, we found that to be 42 degrees. Well, that's it. Lastly, let's tackle this question. It says, what are the direction angles of a vector pointing equally away from the x, y, and z axis? So we'll look for some vector v, which has a magnitude and some direction, and we'll look for what those direction angles would be for such a vector. So if it points equally away from the x, y, and z, what I mean there is that alpha and beta and gamma all equal the same thing. Let's call it theta. So because this is a unit vector, and v would just specify any direction, this magnitude of v would specify any magnitude. This uniquely determines a direction, but let's suppose the direction was equal in each of those angles to each of the axes. So since we generally have cosine squared alpha, cosine squared beta, and cosine squared gamma always equal 1, what would happen if all the angles were equal? Cosine squared theta, and cosine squared theta would have to equal 1. So we'd have 3 cosine squared theta equal to 1, which implies that cosine squared theta is 1/3, or cosine of theta could be either plus or minus the square root of 1/3. That is, cosine of theta could be plus or minus 1 over root 3, and I could rationalize that cosine theta equal plus or minus square root 3 over 3. Now, what angle gives you that value? It's not any of the special angles. We'll have to do cosine inverse. And actually there are two possibilities here, so we look for cosine could either be root 3 over 3, or it could be negative root 3 over 3. So either theta could be cosine inverse of the positive root 3 over 3, or it could be the angle could be cosine inverse of negative root 3 over 3. Can answer in degrees or in radians, but degrees are easier to visualize, so let's find this cosine inverse. So what I get here is about 54.7 degrees. And how about this one? This is about 125.3. So how does this make any sense? Well, what you're seeing is two answers that are supplementary, right? If you took 54.7 degrees plus 125.3 degrees, that makes 180. And so these are two angles that are both correct. Let me look back exactly what was the question. It says, what are direction angles of a vector pointing equally away from the x, y, and z? And the answer is it's either the 54 or the 125. And these are related in this way, and I'll explain a little bit more geometrically what that is. All right, so here I'm using Mathematica to try to visualize these two vectors. So the blue one, the blue vector, is a vector that goes to the point 1, 1, 1. And I guess that's kind of, what is that, sort of a kind of maroon or sort of a darker red. That one is the vector that goes to -1, -1, -1. And these vectors, these three, are the unit vectors I, j, and k. So this is pointing, this is the green is the unit vector I, 1, 0, 0. Blue is 0, 1, 0, is pointing down the y-axis. This is purple one is pointing up the z-axis. This is the unit vector k. So you could see that the angle from the blue vector to these three vectors is the same. It was that, what was it? I had about 54.7. So these are three angles that are each 54.7, but there are also three angles of 125 that are the angles from this sort of maroon color that measure back to the I and the K and also to the J unit vectors. So those are my two vectors that we find that have those angles as we solve for, and they are supplementary. The angles are supplementary, and the vectors are parallel but opposite directions. All right, so that's it. Hopefully that was helpful and interesting.